You can get started now, I think, just because if we run a little bit early, then we can catch up later.
Okay. Hello, everyone. I'm very happy to be the chair of this session, and I would like to introduce our speaker, Chunyan Wang from Beijing, China. And she graduated from Nankai University, Tianjin, China, with a degree in statistics. And her research interests include experimental designs, computer experiments, and the order of addition experiments. Her supervisor is Professor Mingqian Liu. During her PhD study, Chunyan Wang visited the University of Tennessee, USA, and worked under the supervision of Professor Robert Mee. After completing her PhD, Chunyan Wang joined the Department of Statistics at Purdue University as a postdoctoral research assistant in July 2021 and continued her research work in statistical experiment design under the supervision of Professor Dennis Lin. Then she joined the School of Statistics of Renmin University of China as an assistant professor in August 2022. Now, Chunyan has published 6 papers on Annals of Statistics, Statistica Sinica, Journal of Quality Technology, etc. And the title for her today's talk is A New Class of Orthogonal Space Filling Designs. Let's welcome Chunyan Wang.
Hello, can you hear me?
Yeah, sure.
Okay, I'll share my screen. Okay. Okay, this is Chunyan Wang, and I'm so happy to be here to have the opportunity to share some recent work with you all. And the talk I will give today, the topic is a new class of orthogonal space filling designs. So this is an topic in the design of experiments. So it's my research interest in my PhD and my postdoc career. So this work, it is a joint work with Professor Dennis Lin in Purdue University and Professor Mingqian Liu in Nankai University. There is 4 parts of the talk in total, and the first part is introduction. So we want to show how this work, how the background of this work, the motivation of this work. So as we all know, experiments is very important in every field. And it can be divided into physical experiments and computer experiments. So in a physical experiment, the experimenter conducts the experiment on site and collect the data for the analysis and get some inference to guide how we will do in the next step. So it's a very classical experiment type. The computer experiments, it is different in computer experiments. So the experimenter input the variable and get the output from a system. So this system can be a computer. So in other words, in a computer experiment, the experimenter didn't conduct a real experiment. They just input the variable and get the response from a system. So for computer experiments, there is no noise for the same input, we will get the same response. So this is the definition of physical experiment and computer experiments. So with the development of computer science, the computer experiments has gained more and more attention recently. And this paper was focused on the computer experiments. And for computer experiments, there is a lot of designs we can use. So how to choose the desirable design we want? So this is a very important issue. There are many criterions for ranking computer experimental designs. So on one hand, if we know what our model looks like, then the design with orthogonality is preferred, since for an orthogonal design, every two columns are column orthogonal. That means the correlation between them is 0. So if we know the model we want the design has an orthogonality. So on the other hand, if we have no information on the model, it's a very natural way to spread the design point on the design field uniformly. Well, the uniformity can be evaluated by some distance or discrepancy based criterion, or we can evaluate the designs by the low dimensional stratifications. Here is some recent work on the design with low dimensional stratifications. So the first tab is leading hypercube designs. For an leading hypercube design with n ranks, each factor has n levels. That is, each column has the maximum projection on each factor. So it achieves the maximum stratification on one dimension. The second tab and the third tab mappable nearly orthogonal arrays and strong orthogonal arrays. There are new kind of arrays based on the ordinary orthogonal arrays, but they have more space filling properties than the ordinary orthogonal arrays. There are also two other types, orthogonal strong orthogonal array and general strong orthogonal array. They are a tension of the ordinary strong orthogonal arrays. Here we have other full papers on the designs with distance-based criterion. That means the designs in this paper has very good performance under the distance-based criterion. So they are very suitable choice for computer experiment. So here is the subject of this paper. That means we want to construct some designs that with desirable orthogonality, and we want the design can accommodate a large number of columns, and the design has good stratifications in 2 and 3 dimensions. So let's see and illustrate examples. So we can obtain a design labeled X. It can be divided into 8 groups of 2 columns each, and it has the following desirable properties. So in summary, the design has desirable space filling properties are preferred, and the subject of this paper is to construct this type of designs. And in this example, the design we constructed has the following desirable space filling properties. So the first one, any 2 columns achieve stratifications on an 2 times 4 and 4 times grid. The second one, any 2 columns from different group achieve stratifications on 2 times 8, 4 times 4, and 8 times 2 grid. The last one is any 3 distinct columns from 2 different groups achieve a stratification on a 2 times 2 times 2 grid. So it may be very complicated, but we can see it in this way. So this is figure 1. Figure 1 means that it's clear that figure 1 shows the stratifications of the first 2 columns of design X. A design is essentially a matrix. So we have a matrix X, and we selected the first 2 columns of this matrix, and we can draw the plot, and it shows the stratification of this 32 point, means 32 ranks. So we can divide it by 2 times 4 and 4 times 2, and in each plot we can see that the designs uniformly spread in the design region, right? So it means each grid has 4 points. So each grid has 4 points. So figure 2 shows the stratifications of the first and the third column of X. That means we can see that the point is the same. The different lies the way we divided the experimental field. So figure 2 shows that the first and the third column, these 2 columns achieve the stratifications on a 4 times 4 grid, 2 times 8 grid, and 8 times 2 grid. That means for the 3 grouping method, so that each grid has 2 points. That means, in other words, the design point was spread on the field very uniformly. Now here is an stratification of the first 4 columns of these designs. We can see that the design point are very uniform. So it's a kind of uniform designs. So the second part is the construction of the space filling designs. So in first section, we show that we want to construct the designs with good space filling properties. And in section 2, we show how we can construct such designs. So the detail of the construction method may be a little complicated, but we summary this 3 algorithms here. So this paper proposes 3 algorithms for constructing orthogonal space filling designs with 3 types of factors. And the tools are expensive replacement method and general rotation matrix method. So these two methods are very classical in the design of experiments, but we use the method into different situations and different way, so we can get some new results. So here is our algorithm 1. So construction of space filling designs. The main idea is to divide the column of a matrix into different group. And for the column in the same group, we use the rotation matrix method. Then we can get a matrix, and this matrix can be divided into different groups. And for the designs obtained from algorithm 1, we have the following result, theorem 1. So design X from algorithm 1, first of all, it is column orthogonal. It means any two column has correlation 0. And the second, it can be divided into compact groups of mu column each. And after this grouping method, the design columns has the following desirable space filling properties. Here is the algorithm 2. Similar to algorithm 1, we use the grouping method and rotation method, but we just rotate two columns each time. So in algorithm 1, we rotate 4 columns in each time. So here is the difference. And the resulting designs, design Y from algorithm 1 is also orthogonal and has the following desirable space filling properties. Here is the last algorithm 3. So in algorithm 1 and 2, we construct designs that are symmetric. That means each column has the same number of levels. But in algorithm 3, we constructed designs that are mixed levels. That, in other words, the different column of the resulting design from this algorithm can have the different number of levels. So here is the supported for this for the design W. It is also orthogonal, and the column of this matrix can be divided into different groups. And under this grouping method, the design columns achieve the following desirable space filling properties. So here is third section, construction result. So in section 2, we propose many construction methods and give the algorithm code. In third section, we give the detail of the designs we constructed. So table 1 shows the designs we can obtain from algorithm 1. So based on the source designs A and B, so there are two types of orthogonal areas. Based on A and B, we can get design X. Design X is a column orthogonal designs with desirable space filling properties. And their space-filling properties can be evaluated by the kappa, mu, and pi. So the ideal pi is 1. So pi means the proportions that achieve the corresponding stratifications. We can see that the values of pi are very close to 1. It means that they are very close to the ideal designs. So table 2 gives the comparisons of the proposed designs in the first row. These designs are the designs from algorithm 1, and these 4 rows are designs in the literature. So we can see that very clearly that our designs has desirable orthogonality and stratifications than the other 4 types of designs in the literature. Furthermore, the design from algorithm 1 enjoy better space-filling properties, and they can accommodate much more columns than this type of designs. So to sum up, the proposed designs enjoy better space-filling properties, and it can accommodate much more columns. So they are very competitive choice for computer experiment. In table 4 and table 5, we give other resulting designs from algorithm 2 and algorithm 3. So the space-filling properties are similar to that obtained from algorithm 1. So we didn't give more details on that. So here's the last section summary. Combine the first 3 sections. We give the motivation, we give the construction method, and we give the construction result of the method. The summary, we conclude this talk on the subject of this paper. In other words, we propose a new kind of designs, and this designs perform well under the following aspect. The first one is the designs has very the designs are orthogonal. That means every 2 columns has correlation 0, and they are space-filling. That means they have very good stratification properties. And the last one is compared with other designs in the literature. So for given range size, our designs can accommodate much more columns. So in other words, we can arrange more factors in the proposed design. So all these are very ideal properties for computer experiment. Oh, that's all. Thank you. So, and do you have any comments or questions?
As time is running short, little bit, though we still have actually 5 minutes before the next session starts. I've been asking speakers and attendees if they have questions to use the question and answer feature, because attendees cannot really ask you a question directly because there is no way to communicate through that. So let us check and see if people are asking you questions through the attendee question and answer. I don't see any questions yet. Okay, and also Shanian's email is also here. So if people have questions, please feel free to reach out to her during, but it is a great talk and it's really interesting to kind of hear about computer designs, which is the new sort of dimension of designs too. So others question, I will let the speakers in for the next session.
Okay. Thank you all. I'm very happy to join the conference and see you all